Good day, everyone, and welcome to where we are putting together solutions to those math and science areas that students are getting problems with. In this video, we'll be looking specifically at CSEC Mathematics and the topic of matrices. We'll be solving the past paper questions from May 2014 until 2018. Feel free to like the video and add any comments down below so we can make other videos to help you in whatever areas of CSEC, Form 5, or CAPE that you are getting problems with. Don't forget to take a look at the description down below so you can follow the order to get the best results that you have to study the CSEC Maths syllabus so you can get a better grade and a better understanding. Let's look at the major topics in CSEC Math, and we can see that there are 10 of them, and we're concentrating on topic number 9, vectors and matrices, in this video. This topic comes for 4 questions in the multiple choice, paper 1 out of 60, and for 12 marks out of 100 in paper 2. This video deals with past paper questions from 2014 up to 2018. In 2014, it was the last year in which it was given as a question paper of approximately 12 pages long, and we had to write our answers on a different examination pad. From 2015 onwards, spaces were provided on the question paper to write our answers. And from 2018, it changed the format to the present day one, in which there were only 10 questions on the paper, all 10 being compulsory in paper 2, and the marking scheme as identified there. May 2014, number 11, part A. The matrix M is defined as M is equal to 7, 2, P minus 1. Determine the value of P for which the matrix M does not have an inverse. If a matrix does not have an inverse, it means its determinant is equal to 0. So let's recall how we find the determinant. Let's say for any matrix A, any 2 by 2 matrix, the values will be A, B, C, D. And to find the determinant of A, or mod A, which both mean the same thing, it will be multiplying the red terms, the ones on the major diagonal, A by D, and subtracting it from multiplying the green terms, B by C. So we have AD minus BC. So let's apply it to what we have now. So the matrix M is equal to 7, 2, P minus 1. So the determinant of M is equal to, that's right, 7 multiplied by minus 1. That's the red terms minus P multiplied by 2. Let's recall that when you're writing the examination, that there are no colors except black in print. So we're putting colors here in order for you to be able to identify it easier and to see the pattern. So what's the determinant of M? 7 by minus 1 minus P by 2. So that gives us, and we know the determinant is 0 for it not to have an inverse. So 0 is equal to minus 7 minus 2P. And we can carry the 2 minus 2P across. It will become add. So 0 plus 2P is equal to minus 7. So that means 2P is equal to minus 7. And if I want P, carry the 2 across. The 2 is multiplying. When it goes across, it will be the multiplicative inverse, or it means a divide. So it will give us minus 7 over 2. So that will be the value of P in order for this matrix M to have no inverse. Let's look at part B now. Express the equations, and we can see 2 simultaneous equations here. 4x minus 2y is equal to 0, and 2x plus 3y is equal to 4, in the form ax equal to b, where a, x, and b are matrices. Now, let's recall that the steps to solve the simultaneous equations, the first step will be to do exactly this, to write it in that form. So let's extract the coefficients of the terms of x and y and write it as a 2 by 2 matrix. So we have how many x? 4. And then how many y? Minus 2. And then in the next line, we have how many x? 2. And how many y? 3. That's why we get the first matrix, 4 minus 2, 2, 3, by xy equal to 0, 4. As such, the first 2 by 2 matrix is A. xy will be x. and 0, 4 will be B. And we've solved it. May 2015, number 11, A. Part 1. Calculate the matrix product AB, where A is 1, 1, 2, 3, and B is 1, 2, 0, 1. So what they're asking us to do is multiplication of two 2 by 2 matrices. So let's recall, if we had two matrices, P and Q, in the form A, B, C, D and E, F, G, H. Notice I've put different colors for them. Let's remember that it is multiplication. We're using the rows in the first matrix multiplied by the columns in the second matrix. So in the first matrix, I've put the rows in different colors, black for the first row, blue for the second row, and the columns red for the first column in the second matrix, and green for the second column. So how do we multiply PQ? Well, we take the first row, which is in black, multiplied by the first column, which is in red. So it'll give us AE plus BG. Now we've gotten that, let's take the first row by the second column. So it'll be black by green, and it'll give us AF plus BH. And similarly for the second row, using CD and EG, and CD and FH. Let's apply it to this question. So AB would be equal to 1, 1, 2, 3 by 1, 2, 0, 1. And I've put the same colors, so you can just follow to suit. So it will be 1 by 1 plus 1 by 0 for the first value. The second will be 1 by 2 plus 1 by 1. And then below would be 2 by 1 plus 3 by 0. And then 2 by 2 plus 3 by 1. And we can simplify that. 1 ones are 1 plus 1 zeros are 0. And 1 2 is 2 plus 1 ones are 1. Then 2 ones are 2 plus 3 times 0 is 0. And then 2 twos are 4 plus 3 ones are 3. And we can simplify. 1 plus 0 is 1. 2 plus 1 is equal to 3. 2 plus 0 is equal to 2. And 4 plus 3 is equal to 7. So we found AB. Part 2. Show that the matrix of A and B is not commutative, which means that AB is not equal to BA. So we have already found AB, 1, 3, 2, 7. What we really need to do is find BA. Let's reverse the multiplication. So we put B in front, 1, 2, 0, 1, and A in the back, 1, 1, 2, 3. And I've maintained the same colors. It's the rows of the first matrix, so the rows of matrix B that are important. So we have them in black and blue again. And the columns of the second matrix, the columns of A. Quite opposite to the first effort in part 1. So we do the same multiplication, black by red, 1 by 1 plus 2 by 2. And then black by green, 1 by 1 plus 2 by 3. And then blue by red, 0 by 1 plus 1 by 2. And then blue by green, 0 by 1 plus 1 by 3. And we can simplify this. 1 ones are 1 plus 2 times 2 is 4. And then 1 times 1 is 1 plus 2 times 3 is equal to 6. And then 0 times 1 is 1 and 1 times 2 is 2. And then 0 times 1 is 0 and 1 times 3 is 3. And we can solve now. 1 plus 4 is 5. 1 plus 6 is 7. 0 plus 2 is 2. 0 plus 3 is 3. And if we compare AB and BA, we can see that they are not the same. We don't even have to look at all 4 items. We could look at one item alone. As long as one item is different in both 2 by 2 matrices, then you know they're different. So AB is not equal to BA. So we have proven that matrix multiplication is not commutative. And when you have completed a proof, we can write QED, which means quod erat demonstrum, which shows that we have completed the proof. Or if you don't want to write that, we can write a small square, right, to indicate the same. We can simplify our solution in order to prove whether or not AB is not equal to BA by just looking at each element. Instead of working out the entire 4 elements, we could have worked out just the first element alone. We got 1 plus 4, and that gave us 5. And if we compared AB to BA, in AB, the first element was 1. In BA, this first element is 5. Therefore, AB is not equal to BA. However, if they were equal, for some reason, Then we'd work the second element to see if they're the same, and then the third, and so on. As long as any one of the elements are not the same in both of them, then that proves that AB is not equal to BA. May 2015, number 11, part 3. Find A inverse, the inverse of A. And we already were given what A was in part A. So if we're finding the inverse, let's look for the steps for that. First step, find the determinant. So how do we find the determinant? Let's recall that if we have a matrix P with values A, B, C, D, then the determinant of P or mod P would be the red terms, the major diagonal A times D minus the minor diagonal, the green terms, B, C. So let's apply that. Let the matrix A be 1, 1, 2, 3. Well, that's given. So what's the determinant of A or the modulus of A? It will be the red terms 1 by 3 minus 1 by 2. And let's see if we could simplify. 1, 3 is 3 minus 1, 2 is 2. So 3 take away 2 is 1. So the determinant of A is 1. Now what's the second step? Find the adjoint of the matrix. So if we have the matrix P, A, B, C, D, what is the adjoint? The adjoint of a matrix is another matrix with the terms rearranged accordingly. So how is it rearranged? We switch the red terms. So D and A switch. And the green terms, the ones on the minor diagonal, we change the signs. So we get D minus B minus C, A. So let's apply it here. Matrix A is 1, 1, 2, 3. So if we want to get the adjoint A, so this new reformed matrix, we will switch the 1 and the 3, and the green terms change their signs. So we'll get 3 minus 1 minus 2, 1. Last part, find the inverse of the matrix. So how do we do that? So if we have the matrix P, then P inverse will be 1 over the determinant, whatever value we got, multiplied by the adjoint matrix or the adjoint P. So let's apply that. Matrix A inverse would be 1 on the determinant of A multiplied by the adjoint A. So matrix A would be 1 over 1 because we got the determinant above as 1. Multiply what is the adjoint? 3 minus 1 minus 2, 1. So the matrix A inverse would be 1 over 1 is 1. So you could ignore that. So that's be 3 minus 1 minus 2, 1. Part 4. Given that M is equal to 2x by 2, but 3, 9, and 3, calculate the values of x for which the determinant of M is equal to 0. So we already have that format in part 1, how to work out the determinant. So let matrix M be 2x, 2, 9, 3, and follow the format again. Multiply the red terms, 2x by 3 minus 9 by 2. And we're saying that the determinant is 0. So it'll be 0 is equal to 6x minus 9 to 18. And if we want to solve for x, we take the minus 18 and carry it across. So we get 0 plus 18 is equal to 6x. So that means 18 is equal to 6x. And if you want to find for x alone, the 6 is multiplying on the right-hand side. When we carry it across, it will do the opposite, multiplicative inverse or division. So 6 into 18 would be 3. So x is equal to 3. When we substitute x is equal to 3 above, we can see 6 by 3 is 18 minus 9 2s are 18. The determinant works out to be 18 minus 18 is 0. So it works out. May 2016, number 11, part B. Determine the value of x for which the matrix 3x 2, 4 is singular. And what does that mean? It means that the determinant of a singular matrix is 0. So let's recall how do we find the determinant of a matrix. So matrix A will be equal to A, B, C, D. And if we want to find the determinant of A or mod A, modulus of A means the same thing. It will be the red terms on the major diagonal AD minus the green terms BC. And this is the format for finding the determinant of 2 by 2 matrices. So let's apply it to our question. So let some matrix M be equal to 3x2, 4. So the determinant of M or mod M would be the red terms 3 times 4 minus the green terms 2 times x. And we know that it is singular, so the determinant is 0. So So 0 is equal to 3 fourths are 12 minus 2x. And we can carry the 2x across. It's taken away on the right hand side. When I carry it across, it will add. So we'll have 0 plus 2x is equal to 12. So 2x is equal to 12. And if you want to find x alone, the 2 is multiplying. When I carry it across, the opposite of multiplying will be dividing. 12 over 2. 2 into 12 is 6. As such, x is equal to 6 in order for this matrix to be singular, or to have a determinant of 0, or to have no inverse. They all mean the same thing. Now for part C, N and P are 2 by 2 matrices such that N is equal to 4132 and P is equal to 1521. Determine NP. So what they're asking us to do is recall, first of all, we must recognize how to multiply two 2 by 2 matrices. So let's recall AB is equal to ABCD and EFGH. And multiplying matrices like these, we need to multiply the rows of the first matrix by the columns of the second matrix. So I have them in the colors black for the first row and blue for the second row, and for the columns it will be red for the first column and green for the second column. And if there was a third column, then we'd have that in a different color as well. So row by column, first row by first column, black terms by red terms, AE plus BG. Then first row by second column, black by green. So AF plus BH. And then blue by red, which will give us CE plus DG. And second row by second column, blue by green, CF plus DH. And let's apply to NP, our question. So we have 4132 by 1521. I've maintained the same colors as above, so you can follow the pattern. So it'll be 4 times 1 plus 1 times 2. And then for the second item, 4 by 5 plus 1 by 1. And then blue by red, 3 by 1 plus 2 by 2. And then blue by green, 3 by 5 plus 2 by 1. And we can simplify. 4 ones are 4 plus 1 by 2 is 2. So that's for the first item. And then 4 by 5 is 20 plus 1 by 1 is 1. And then 3 by 1 is 3 and 2 by 2 is 4. And then 3 by 5 is 15 and 2 by 1 is 2. So 4 plus 2 is 6. 20 plus 1 is 21. 3 plus 4 is 7. 15 plus 2 is 17. And that is NP. Now part 2. Given that Pn is equal to 19, 11, 11, 4, determine whether matrix multiplication is commutative. If it is commutative, it means that NP, N times P, would be equal to P times N. And we can see that NP is 6, 21, 7, 17, and is different from Pn. So NP is not equal to Pn. So matrix multiplication is not commutative. May 2016, number 11C, part 3. Determine the inverse matrix of N. Now they gave us M. N is 4132 from the previous parts. And what are the steps for inverse? First, find the determinant. So let's recall for some matrix A, B, C, D. Generally, the determinant of A or mod A would be the major diagonal terms when you multiply them minus the minor diagonal terms when you multiply them. So we have them in red and green, so it will be AD minus BC. And let's apply that to our question here. So the determinant of N would be the red terms 4, 2 minus the green terms 1, 3. So the determinant of N would be 4 2s are 8 minus 1, 3 is 3. 8 minus 3 is 5. So we found the determinant. What's the next step when we're finding the inverse? We must now find the adjoint of the matrix. So let's recall for the matrix here, ABCD, the adjoint of the matrix really means another shift, but another matrix. So how are we shifting it? The major diagonal terms A and D are switched, so it become D and A, and we change the sign on the minor diagonal on the green terms. So let's apply it to matrix N. We have 4, 1, 3, 2. So the adjoint would be switching the red terms. So the 2 will come up on top and the 4 will go below. And the 1 and 3 will change their signs to become -1 and -3. So we've gotten the first two steps. The final step is to find the inverse of the matrix. So to find the inverse of a matrix, we have 1 over the determinant multiplied by the adjoint of the matrix. So let's apply it to here. So the matrix n inverse, the inverse of the matrix would be 1 over mod n, 1 over the determinant, multiplied by the adjoint matrix. So that will be 1 over 5, because we got the determinant as 5, multiply, it's understood, so we don't need to write it, 2 minus 1 minus 3, 4, the adjoint matrix. Part 4 now. Hence, meaning that we can use what we've just worked out in part 3 for n inverse, calculate the values of x and y for which 4, 1, 3, 2, xy is equal to 1, 2. And this would be two simultaneous equations that we have to solve. So just like in number 2 of the past papers, in paper 2, you will find that they usually bring a simultaneous equation there, two linear equations. This is another method to solve that. So some of our students use this method to solve that question over in number 2 of the past papers in algebra, because they don't specify which method. So they learn one method and apply it to two different questions. So let's see. 4, 1, 3, 2, let's consider that is the matrix n times xy, that column vector, we'll call that x, equal to 1, 2, and we'll call that b. So nx equal to b, and if that's the steps to solve our simultaneous equations, we've just done step 1, which is to write it in the form ax equal to b. Step 2, pre-multiply on both sides. So if we pre-multiply by a inverse on both sides, it will be able to remove the a and carry it across. So let's do that there. Nx equal to b, so n inverse n by x is equal to n inverse b. Part 3 now, simplify. So how do we simplify? N inverse n, when we have two matrices multiplying by each other and one is the inverse of the other, then we will get the identity matrix I. So Ix is equal to n inverse, we already have that from part 3, 1/5 by 2 minus 1 minus 3, 4, by b, and we know b is 1, 2. So now that we have substituted here, we can simplify and solve, which is part 4, our fourth step in solving simultaneous equations. So Ix, when you have the identity matrix multiplied by another matrix, then it's like multiplying by 1. It will give us this x, the matrix itself. So x is equal to 1/5. And how do we multiply a 2 by 2 matrix by our 1 by 2 matrix? Well, we multiply rows by columns again. So we have in the first matrix, the rows in two different colors, black on top and blue below. And we have the column in red. So multiplication will be black by red, the first row by the one column, the first column. So 2 by 1 plus minus 1 by 2. And then the second row by the column. So it will be minus 3 by 1 plus 4 by 2. So 2 by 1 is 2, and minus 1 by 2 is minus 2. And then minus 3 by 1 is minus 3, plus 4 2s are 8. So we're simplifying. And that gives us x equal to 1/5 by 2 minus 2 is 0, and minus 3 plus 8 is 5. And we can multiply by 1/5 for each term. And what is x? X are the two values x and y. So that will be 1/5 of 0 is 0, and 1/5 of 5 is 1. So that gives us our final answer, that the values, in order for those to work out above the simultaneous equations, x must be 0 and y is equal to 1. We can check here by substituting 0 and 1 in there and work it out, and you will see that you'll get back the two values of b. So your question is perfectly right. May 2017, number 11, A. Matrices A and B are such that A is equal to 3, 2, 5, 4, and B is equal to 4, 0, 3, minus 1. Part 1. Show by multiplying A and B, those two 2 by 2 matrices, that AB is not equal to BA. So let's recall, how do we multiply 2 by 2 matrices? We multiply the rows of the first matrix by the columns of the second matrix. And we've put them in different colors, the first row being black, and the second row being blue, and the first column being red, and the second column being green. So we're multiplying the first row, which is black items, by the first column, red items. So that will give us AE plus BG. And then the first row by the second column, black by green, So it'll give us AF plus BH, and then blue by red, CE plus DG, and then blue by green, CF by DH. So hopefully we can recognize how to do these 2 by 2 matrices multiplications and apply it to this question. So AB, 3254 by 403 minus 1. So 3 by 4 plus 2 by 3, and then 3 by 0 plus 2 by minus 1, and then 5 by 4 plus 4 by 3, and finally 5 by 0 plus 4 by minus 1. And AB, we can simplify. 3 4s are 12 plus 2 3s are 6. And then 3 zeros are 0 plus 2 by minus 1 is minus 2. And then 5 4s are 20 plus 4 3s are 12. And then 5 zeros are 0 plus 4 by minus 1 is minus 4. And we can solve for AB. 12 plus 6 is 18. 0 minus 2 is minus 2. 20 plus 12 is 32. And 0 minus 4 is minus 4. Now that we've found AB, we need to find BE. So let's switch the matrices, and we maintain that in the first matrix, that the top row is in one color black and the second row is in blue, and the first column in the second matrix is red, and then the second is green, because it's still whatever the first row is, the first matrix is the rows by the columns of the second matrix. So BA will give us 4 by 3 plus 0 by 5, and then 4 by 2 plus 0 by 4, and then 3 by 3 plus minus 1 by 5, and then 3 by 2 plus minus 1 by 4, and we can simplify. 4 3s are 12 plus 0 5s are 0, 4 2s are 8 plus 0 4s are 0, 3 3s are 9 plus minus 1 by 5, that'll give us minus 5, 3 2s are 6 plus minus 1 by 4 is minus 4. So 12 plus 0 is 12, 8 plus 0 is 8, 9 minus 5 is 4, and 6 minus 4 is 2. So we solve BA. So let's look at the values of AB. 18 minus 2, 32 minus 4, and BA, 12, 8, 4, 2. And we can see that AB is not equal to BA. So we've proven this. As we are practicing to get perfect at the matrices, I've shown the working for the entire of AB and the entire of BA. But if you look at these yellow rectangles that I've put up here, we actually only need to work out the first element in each and see whether they are the same. In this case, we just needed to work out 12 plus 6. That will give us 18 for AB, and 12 plus 0, which was 12 for BA. So 18 is not equal to 12, therefore AB is not equal to BA, and that was enough. We did not need to work out for all four elements. However, if the first elements happen to be the same, then we work out for the second element in each of them. And if not, if they were the same, then we work out for the third, until we could get at least one element in the same positions in both AB and BA that are not the same. And that proves that AB is not equal to BA. May 2017, number 11A, part 2. Find A inverse, the inverse matrix of A. So let's recall we have some steps for finding the inverse. First step being finding the determinant. So let's recall for any matrix, any 2 by 2 matrix A, B, C, D. To find the determinant, we multiply the major diagonals, which are we have in the red terms, minus the minor diagonal terms, which we have in green. So that will give us AD minus BC. Maintaining the same colors, let's try and solve this question so students can easily follow. So we already know A. It was given in part 1 as 3254. So to find the determinant of A, or modulus A, which means the same thing, the A with two straight lines coming down on either side of it. To solve that, we'll multiply the red terms, 3 by 4 minus 2 by 5, and that will give us 12 minus 10, which is 2. So that's the first step. Step 2 now, find the adjoint of the matrix. So the adjoint matrix is another matrix in which the first the terms were rearranged. So how do we rearrange it? Well, we switch the major diagonals, or the red terms, so the D is up on top and the A is down below, and we change the signs of the minor diagonals, of the green terms. So we'll get D minus B minus C, A. So let's do that here for this question. So matrix A is 3254. So let's find the adjoint of that matrix, so adjoint A would be 4 minus 2 minus 5, 3. We switch the red terms and we change the signs of the green terms. And the final step, find the inverse of the matrix. So how do we do that? We take the matrix and we say 1 over the determinant times its adjoint. So let's apply it here. Matrix A inverse will be 1 over the determinant of A, which we worked out already, times the adjoint of A, which we've worked out already above. So let's just substitute. Matrix A inverse will be equal to 1 over 2, because the determinant is 2, times the adjoint, which is 4 minus 2 minus 5, 3. And we can leave it as is because it's a nice whole numbers. Part 3 now. Write down the 2 by 2 matrix representing the matrix product A inverse. So if we have A inverse, that means that when two matrices are multiplying each other and one is the inverse of the other, it gives us the identity. So A inverse will be equal to I. And what is the identity matrix? 1, 0, 0, 1. And for part B now, write the following pair of simultaneous equations as a matrix. 3x plus 2y is equal to 1, and 5x plus 4y is equal to 5 for 1 mark. So when we are writing it as a pair of matrix equations, then what we are doing is extracting the coefficients, the numbers in front of the letters. So what number is in front of x? 3, and in front of y? 2, and in front of x again? 5, and in front of y again? 4. So we have 3, 2, 5, 4 by xy would be equal to 1, 5. And we know 3, 2, 5, 4, that is the matrix A. xy, that column vector, we'll call it matrix X, and that will be equal to B, which will be the matrix for the column vector 1, 5. And this is the first step to solving simultaneous equations, where we've written it in the form Px equal to B. In part 2, write the solution of your matrix equation in B part 1 as a product of two matrices. So we've already looked at it and recognized that we have Ax is equal to B. So let's look at the second step in solving simultaneous equations, which would be to get rid of the P by multiplying by P inverse on both sides. So let's do the same thing here. So if we have Ax equal to B, let's multiply by A inverse on the left side and A inverse on the right side. So we have A inverse Ax is equal to A inverse B. How does that help us? Well, A inverse by A, as we worked out in part 3, was the identity matrix 1, 0, 0, 1. So we can replace it and say Ix is equal to, and we can substitute for A inverse, which we got in part 2. So A inverse is a half by 4 minus 2 minus 5, 3 by B, 1, 5. And I by X, the identity matrix by another matrix, will just give us the X. And we know X is the X and Y values that we need to solve the simultaneous equations for. So XY is equal to half by 4 minus 2 minus 5, 3 by 1, 5. And that is actually our solution, because they ask us only to find the product of two matrices. However, I've gone on and worked out, and you should practice as well, to work out the actual values of X and Y, which worked out to be minus 3 and 5. May 2018, number 10. A transformation T is defined by the matrix T is equal to 2, minus 1, 2, 0. And when we say a transformation, it's similar to rotation or reflection. The point A, minus 2, 3, is mapped onto the point A prime, which we don't know. We don't know its X and Y values, and they're represented by A and B under the transformation T. So find the values of A and B in part 1. So TA is equal to A prime, and T is 2 minus 1, 2, 0, and we know A, minus 2, 3, and this will give us A prime. So let's multiply these together. Let's recall that when we are multiplying matrices, we are multiplying the rows of the first matrix by the columns of the second matrix. So the first row is in black, so it's 2 by the column in the second matrix, minus 2, so black by red, plus minus 1 by 3. And the second row is blue by red. So it's 2 by 2 plus 0 by 3. And we can simplify that, and that will give us 2 by minus 2 is minus 4, plus minus 1 by 3 is minus 3. And 2 by minus 2 is minus 4, plus 0 by 3 is 0. And we can solve, so minus 4 minus 3 is equal to minus 7, and minus 4 plus 0 is minus 4. As such, the point A, which is minus 2, 3, was mapped using that transformation T onto its image, A prime, which has the values minus 7 as A and minus 4 as B. Part 2. Determine the transformation matrix that maps A prime to A. So we want to go in the opposite direction. So we know T mapped A onto A prime, and if we want to go backwards from A prime to A, we want to get the opposite of T, or T inverse. So we have some steps for finding inverse. First step, find the determinant. And if we recall from matrix A, B, C, D, and we've put the major diagonal in red, A and D, and the minor diagonal in green, B and C, then the determinant of A, or mod A, is the multiplication AD minus the green terms BC. So let's apply that here. So matrix T is 2 minus 1, 2, 0. And we eventually want to end up with T inverse. So this is our first step. The determinant of T would be the red terms 2 times 0 minus the green terms minus 1 times 2. And 2 times 0 is 0, minus 1 times 2 is minus 2. And minus 2, we have the same sign, so that means I add. So we have plus 2. The plus is not necessary to write, so we could just say the determinant is 2. Step 2, find the adjoint of the matrix. So the adjoint of the matrix T would be shifting of the values of T. So it will be another matrix, unlike the determinant, which was an actual number. So how do we switch it around? We switch the major diagonal terms, the red terms, the D comes up on top and the A goes below. And the green terms, the minor diagonals, we change the signs. As such, if matrix T is 2 minus 1, 2, 0, I have the same colors again, switch the red terms, so the 0 comes up on top, the 2 goes below, and change the signs in the green. So minus 1 becomes plus 1, the plus is understood, we don't have to write it, and 2 becomes minus 2. So finally, find the inverse of the matrix. So how do we find the inverse of the matrix? We say 1 over the determinant times the adjoint matrix. So matrix T inverse would be 1 over determinant of T times the adjoint of T. And we know determinant of T is 2 and know the adjoint. So let's substitute. Matrix T inverse would be a half times 0, 1, minus 2, minus 2. And we can leave as is, or if you want, you can multiply it out. May 2018, number 10, A, part 3. Another transformation P is defined by the matrix P is equal to 0, 1, 1, minus 2. So part A, find the single 2 by 2 matrix that represents a combined transformation of T followed by P. So let's recall, if we're saying that two transformations are one following the other, it means multiplication of two 2 by 2 matrices. So let's look at, recall AB as an example, ABCD for matrix A and EFGH for matrix B. And if we're multiplying two 2 by 2 matrices, the rows by the columns. So the black rows by the red column, AE plus BG, and then the black row by the green column, AF plus BH, and then the blue row by the blue column, CE plus DG, and finally the blue row by the green column, CF plus DH. So let's apply that to this question. Now, the only trick in this question is whether it is PT or it's TP. Take your time and take a look at it and let's see. It's the combined transformation of T followed by P. Means T is acting first and then P. In matrices, if it's acting first, it will be on the right-hand side. So we'll write it as PT. T acting and then followed by P. So let's substitute accordingly. We know P. P was given above, 0, 1, 1, minus 2. And T was given previously as 2, minus 1, 2, 0. So let's multiply black rows by red columns, 0 by 2 plus 1 by 2. Black rows by green columns, 0 by minus 1 and 1 by 0. Blue row, second row by first column, 1 by 2 plus minus 2 by 2, and then 1 by minus 1 plus minus 2 by 0. We can simplify PT now. So 0 by 2 is 0, plus 1 by 2 is 2. 0 by minus 1 is 0, plus 1 by 0 is 0. 1 by 2 is 2, plus minus 2 by 2 is minus 4. 1 by minus 1 is minus 1, plus minus 2 by 0 is 0. And we can solve for PT. So 0 plus 2 is 2. 0 plus 0 is 0. 2 minus 4 is minus 2, and minus 1 plus 0 is minus 1. So we've solved for PT, the combined transformation. That is, if we had a point, we acted on it by transforming it using the transformation T. And then when we got this new point, we transformed it again using P. So instead of doing it in 2 steps, we could have done it in 1 step, which would be 2, 0, 0, minus 2, minus 1. So PT would give us that total movement in one go. Let's look at part B. Hence, find the image of 1, 4, that point, under this combined transformation. So let's look at the image of PT acting on a point 1, 4. So instead of going step by step, we could go straight across with this combined 2 by 2 matrix. So what's PT? 2, 0, minus 2, minus 1 by 1, 4. Remember, we're changing the row vector 1, 4 to a column vector. No commas are needed, no division lines, anything. Now, how do we multiply these? Take your time and take a minute to think about it. So when we're multiplying two matrices, we multiply the rows of the first matrix by the columns of the second matrix. So we have a black row by a red column, and then a blue row by a red column. So 2 by 1 plus 0 by 4, and then minus 2 by 1 plus minus 1 by 4. And that will give us 2 ones are 2, plus 0 by 4 is 0. And then minus 2 by 1 is minus 2, plus minus 1 by 4 is minus 4. So finally, we can solve for the image, which is where this new point is going to end up. And it will end up at 2 minus 6. This is the end of the video on CSEC past paper questions on the topic of matrices. In our last video, we did 5 years past papers from May 2009 to 2013. And in this video, we've done from 2014 to 2018. Our next video, we will be working on past paper questions from 2019 to the present. Feel free to take a look at the description down below, so you can follow the order we recommend in order to go through all the videos with their solutions, so that you can get a better understanding of the CSEC Math past paper questions and therefore get a better grade.